Okay, Thermo 1 team, let's go ahead and get started. We are, hello? Please mute. Okay, so we are midway. We're one lecture into chapter 4. We've been pretty much through the conservation of mass, the principle. I've added a few slides here, and so I sent out the chapter 4 PowerPoint again this morning, and I will be making additional changes, additions to it as we go through the chapter, so expect to receive more copies of it from me. This is the last slide that we went through in class last time. Just talking about mass flow rate, one-dimensional flow, which has some simplifying assumptions about properties coming into and exiting a control volume. I mean, we assume that flow is normal to the boundary. So we're going to take that normal component of velocity if we're going to use a velocity times an area to calculate a volume flow rate. All intensive properties are uniform with position, so they can change, but at a particular position, they are uniform. And so anyway, and then this little expression, this gets used a lot. And so the area, cap A is the area that you have this flow coming through. V is the normal component of velocity that's bringing the flow through the area. So if you look at units, you got meters squared times meter per second, just in the AV term, and so that's meters cubed per second. And then if you're going to get to a mass flow rate, you've got to have either density or specific volume. So we're going to divide by the specific volume of the fluid, and that's going to convert from meters cubed to, say, kilograms, or from cubic feet to pounds mass if you're in the US system of units. So anyway, that's just a bit of a review from last time. But what I did go back and I added this integral formulation. This is in the text. It was not in the slides, and so I want to cover it briefly. It's not a big deal, but conceptually, to get you prepped up for your future classes, it's good to be introduced to and comfortable with these integral formulations. So we want to consider the mass rate balance expressed in local terms, and by local terms that means that things can change across that inlet or within that control mass. It's just that they're constant with position. The total mass contained within the volume at any instant t, so this is evaluated at some point t in time, can be related to the local density as follows. And so that's why we call this the integral formulation, because everything winds up to be an integral. You know, that makes pretty much sense. So the mass in a control volume at any time t can be calculated if you know this density function, by taking that density, which is the density at every little dV, and then multiplying it by dV, and that's the local dm, and then we integrate that all over the control volume, and we come up with the total mass. So just using the concept of an integral is, for a more sophisticated analysis, sometimes if you want to take that density variation into account, you have to approach it this way. You have to do that integral. Now, the trick is knowing the density function. And that's probably not an easy trick. And we don't do that in here, but we just want to show you how, if you had a density function that would give you the density, say, within that control volume, that how you could use it to calculate the total mass in the control volume. Okay? And notice that it is at some particular instant in time. It's like you take a picture of it, you freeze it in time, you get your density function, and you do the integral. And you go, wow, okay, that's how much mass I have in here. Okay, let's get this whole thing up there. Okay, so when we go to the entire mass rate balance equation, you know, the first term on the left is the rate of change of mass within the control volume. So it's just a d dt of that integral. So the integral is how much mass is in there, and then we take d of dt of that, and that's the rate of change of mass in the control volume, okay? And then that has to be equal to, well, the summation of what's coming in minus the summation of what's going out. So it's simple, but you see, I mean, it's such a simple concept, the math can build pretty quick, you know? So we just want to get you used to looking at this. So on the right-hand side, the first term is the summation over the inlets. And, you know, most systems probably just have one inlet and one exit. Okay, well, that's fine. Then you just have one integral coming in, one integral going out. But you could have 3 or 4 or 5 or 10 coming in, and you could have 3 or 4 or 5, 10 going out. And so you have to do that area integral over each one of those inlets. Okay, and so on that, inside the parentheses on the inlet term, we're going to integrate over the area of rho, the normal component of velocity times dA. And again, I encourage you to check the units on these things. When you actually write out the units, it will go a long ways towards you understanding, you know, how these variables are working together. So area, we know, would be meters cubed or feet cubed. Normal velocity would be like meters per second, right? So if you take the V sub n times dA, that's meters per second times meters squared. Well, that's meters cubed per second. So that's a volume flow rate coming across that boundary where we're taking the area that it's flowing through. And then, but we're doing mass, we're not doing volume. So guess what? I got to either multiply by density or divide by specific volume. So density is what? Kilograms per meter cubed. And so when you look at the units on that whole thing, it comes out what? Kilograms per second through that little dA. And then you're going to integrate all around, all over the area. And so you're going to add up all those little contributions, and you're going to get the total amount of mass that's coming in that inlet. So that's what those terms are doing. And then on the exit side, it's exactly the same thing. It's just this stuff is leaving, the other stuff is coming in. And if you've got, you know, different number of inlets and exits, you've got to do each one and add up the results, okay? So that's kind of my off-the-cuff explanation. I think this black text was taken out of the textbook. It says where the area integrals are over the areas through which mass enters and exits the control volume, okay? The product of density times normal velocity is given a term mass flux and gives the time rate of mass flow per unit area. To evaluate the terms on the right-hand side requires information about the variation of mass flux over the flow areas. Yeah, I mean, you can't integrate it if you don't have functions that describe it. Otherwise, you just can indicate it in a general form such as this. Okay, well, I think that's enough of that. So let's move on to the first law for a control volume. And that picture's a little small, but that's what they gave us. So that's what we'll work with. So you can see we've got a control volume, that kind of blob. That could be a balloon. That could be a lopsided balloon. There could be, you know, you could be blowing up a balloon here. There could be just inlet and no exit until somebody pops it, and then there's a tremendous exit, right? And some noise generated and all that. But anyway, in general, we've got this region in space called a control volume, and we got some mass flowing in on one side and coming out on the other. We'll generalize this to more than one, but the picture gets too complicated, so they're just gonna draw one inlet and one exit at this point. We can have heat transfer. You got a Q dot term up there. And so That one Q dot term represents the net heat transfer all around that control surface. So it could be coming in on the top, it could be going out on the bottom, you know. So basically you have to sum up all of the heat transfer effects, and the little arrow is shown, they show the arrows in the positive coordinate direction. So he's showing it coming in because heat added to the system is positive. So he shows the little squiggly line with the Q dot coming in, but that's the net for the whole surface. So, you know, I mean, it could be air conditioning. That could be a room. We could be having, say, 10,000 BTUs an hour gained through the windows, but the air conditioner is a 1-ton air conditioner, which is 12,000 BTUs an hour being extracted. And so the net then would be 2,000 BTUs extracted from the space, which extracted would be a negative for us because we got more going out than we got coming in. You can turn that around whichever way you want to make up the example. Okay, and then you've got the work term, and that's the net. You know, you could have electric resistance, you know, electricity flowing across there as a work term. You can have a paddle wheel. You can have any of our work modes. You could have the boundary, that control volume, like a balloon could be blowing up. And so that boundary, that's PDV work. Any of those work terms. So that cap W dot is the net of all of them considered together, okay? And then we've got some mass that's entering. We got an M dot I, and of course it has energy. You know, how can that matter? You know, how do we express that energy that's in that flow coming in? Well, it has internal energy. It has overall kinetic energy, VI squared over 2, and it has potential energy. So that's the possibility. And we got the same thing on the exit side. So that's about all that's in the picture. Now let's see what he says. Okay, so for this energy rate balance, we're just going to balance up all of that stuff, okay? It's all energy in different forms. And so on the left-hand side, we put the time rate of change of energy contained within the control volume, okay? And all of this is at one particular point in time, you know? You pick T, now take a picture of it, and you evaluate it. And that's what this rate balance equation is going to do for us. So on the left, it's the time rate of change of energy contained within the control volume. And then as the terms on the right, the first term is the net rate at which energy is being transferred in by heat at time T, minus the net rate at which energy is being transferred out by work at time T, plus the net rate of energy transfer into the control volume accompanying mass flow. So that far term on the right takes into consideration both the inlet flow and the exit flow, okay? And so that's the net rate. It could be increasing, it could be decreasing, or it could be staying the same. You know, it just depends. We'll have all kinds of problems. Some will be transient in nature, and you'll kind of curse those because they're harder. And a lot of them are steady state. You'll kind of like those because they're easier, but you know, whatever. Okay, so if we're going to put some math to it, it's pretty much what you'd expect from the picture. So D cap E CV dt. So ECV is the total energy of the control volume at any point in time. And we're going to take the time derivative of that. So that's the rate of change of energy in the control volume, is equal to Q dot, that's our net heat transfer rate, minus W dot, that's our net work rate, taking all the different heat transfers and works into account. And then we're showing just one inlet, so we got M dot I, that's the mass flow rate, kilograms per second, pounds per hour, whatever, kilograms per fortnight, you know, whatever units of time you like. And that's multiplied by the total energy that's coming in, internal energy, velocity, and potential energy. And then the same thing on the exit, times the exit mass flow rate. So, I mean, the equation gets longer, but so long as you just got to follow along and make sure that you're clear about what each one of these terms is, where you go to get it, how you evaluate it, and, it just maybe it's going to take an extra 15 minutes to solve the problem, because you got more terms to play with. Okay. Now work, we're going to do some manipulation on this work term. So I got about 3 or 4 slides here, and this is definitional, but I mean it has a practical outcome. So let's see. Evaluating work for a control volume. Work is always done on or by a control volume where matter flows across the boundary. Now this is new for us, okay? So if you've got matter flowing in or flowing out, there is work associated with that flowing fluid material, okay? It is convenient to separate the work term, which is W dot, into 2 contributions. So we're gonna split this work term into a couple of different pieces here. One is the work associated with the fluid pressure as mass is introduced at inlets and removed at exits. And we're going to call this flow work, okay? The other we're going to call W dot CV, and that includes all of the other stuff that we've been considering in the past. That's the rotating shafts, the displacement at the boundary, the electrical effects, all the different modes of work that we're describing in chapters 2 and chapters 3. All that goes in W dot CV. But the work associated with getting that mass flow into and out of the control volume is going to be split out, okay? So consider the work at an exit. We could pick an entrance, it doesn't matter, associated with the pressure of the flowing matter. Recall, the rate of energy transfer by work can be expressed as the product of a force and a velocity, because work itself is what? A force over a distance. But rate of doing work is a force over a velocity, because a velocity is what? A distance over time. So that turns it into a rate. Okay. Thus, the rate at which work is done at the exit by the normal force due to pressure is the product of the normal force, and pressure times area is force. Pounds per square inch times square inches is pounds, so that's just a force, and the fluid velocity. So that's going to be our flow work term. Thus, we can write time rate of energy transfer by work from the control volume at the exit is the pressure times the area, which is force times velocity. So I mean, if you think about it, again, you can look at units. Pressure, say, pounds force per inch squared, area inch squared. So then that's a force, and then that's a velocity. So pound force foot per second. Well, foot-pound force is work, right? And then if you divide it by second, you've got rate of doing work. So again, I encourage you, write out the units, and then you can even go to the conversion tables and look at how you could convert that to other systems of units, just to kind of give you a warm fuzzy about working with the terms. So here, P sub B is pressure, A sub B is the area, V sub B is the velocity at exit E respectively. Similar expression can be written for the rate of energy transfer by work into the control volume at I. So all you got to do is change the E's to I's, and you got it. Okay, I know it's a lot of hoop-de-doo, but engineers are supposed to understand where things come from. Anybody can write an equation and plug some numbers in it. The engineer is supposed to understand where this stuff comes from. So that's why we pound these definitions and explanations quite a bit. Okay, So now we're going to split that that work term. So the one on the left, just the W dot, that's the whole kit and caboodle. And that's the one we had way back here. See? So right now, that W dot CV plus the flow work is all contained in that W dot. But now we're going to split it out. Okay. And so, you know, I think we've got it pretty well defined, but all the rotating shafts, electricity, and all that stuff's in W dot CV, and the M dot E, PE, VE, then that's the little v now is specific volume. So the big V turned into specific volume, but when you multiply by the mass flow rate, so, you know, that turns it back into a big V. And so we have already said that. And so this M dot E pressure sub E, specific volume sub E, is flow work at the exit E, and we got the same thing at the inlet I. Okay? And so now we're going to substitute all that stuff in, and now you notice that the work term here turned into W dot CV because we included the flow work in here and here. So at the inlet, it's this M dot I times P sub I, specific volume sub I, and on the exit, it's M dot E times pressure sub E, specific volume sub E. Okay? Well, I guess that's good. We're making progress here. Now, enthalpy. Now you see why enthalpy is really defined. Because if you didn't have enthalpy defined, you'd have all these little P sub I, specific volume sub I, and P sub E, specific volume sub E, running around in all of your equations. And some smart engineer back in the day said, hey, these are all properties. Why don't we just combine this internal energy with pressure times specific volume and call it something and tabulate it, and it'll make all our calculations a lot easier. And that's what they did. They called it enthalpy. And so enthalpy is the internal energy plus flow work. And so when you make that substitution, then you get, this is the version, and this of course is for one inlet and one exit, but this is the version of the first law for an open system that we actually are going to use to solve problems with. I mean, most of the time, I don't know. They may be able to construct, they can probably construct something that makes you go back into the definition of enthalpy. But in the real world, 99% of the problems you address with this. Okay, we good? Good. Okay, let's see. In practice, there may be several locations, so we can have multiple inlet and exits, and you know what we do. We just stick in a summation sign, and so at each inlet, you have to evaluate all that stuff. At each exit, you have to evaluate all that stuff. So that's not much to that. So this is the accounting balance for energy of the control volume. So yay, we're making progress, guys. Okay, steady state, control volume, energy rate balance, steady state form. The steady state's a big deal, okay? So when you read your problem statement, you always want to look and see if you can, I mean, steady state is your friend, right? That means dECV dt is equal to 0. That's your friend. It makes the problem easier, okay? So you're always looking for that thing. Assume steady state conditions. There you go. So what that means, all properties are unchanging with time. For steady state control volume, dECV dt is 0. You get to throw that derivative term out. And so, bingo, the first law, open systems, collapses to this. Okay. One inlet, one exit, which is we work lots of problems. We'll work turbines, we'll work pumps, we'll work diffusers, we'll work nozzles, we'll work all kinds of different components, the vast majority of which have one in and one exit. And we can oftentimes consider them at steady state. So the mass rate balance reduces to, if it's steady state, whatever's flowing in has to be flowing out. So m dot 1 is equal to m dot 2, and you don't even really need to put a subscript on it if it's the same all over the place. Okay? And so if that's the case, then we can just factor it out. And so now think about units right now. The heat transfer term that's total heat transfer. Okay? So that's like what, megajoules or kilojoules or, whatever you want, BTUs. Work is the same thing. I mean, they have to all produce the same units or you can't add them together, right, in the same equation. Inside the big brackets, what? Enthalpy is going to be what? Kilojoules per kilogram. See, all of this stuff is per unit mass inside the bracket, but I multiply it by the mass flow rate, which then clears the mass units from all bracket terms. Or, and this, we'll have a sizable number of problems like this. You can also just divide through by the M, and then it's the heat transfer per unit mass. It's the work per unit mass. And then all those other terms are per unit mass. So you can work it for the total mass, or you can work it on a unit mass basis. And some problems require one or the other. But if you see something like heat transfer, like megajoules per kilogram or something, then it just means that they have divided through by the mass flow rate. Okay. Integral form. We want to hit a little bit on this. Total energy, control volume. Yeah, we'll go ahead and do this. Okay. And how are we doing on time? Just check in. Oh, man, we're flying. Let's see, 9:30. Okay. The energy rate balance can be expressed in terms of local properties to obtain forms that are more generally applicable. So again, the integral formulations want to describe everything in terms of these local properties, which means we have to have functions that describe those things. The term energy and the control volume at time t represents total energy associated with control volume at time t. Can be written as a volume integral. And there you go. I mean, it's pretty similar to what we had before. So we've got internal energy, potential energy, and kinetic energy. And so on the U term, that's the one we're most used to looking up. So that is like kilojoules per kilogram. And then the volume is what? Meters cubed. And then the density is what? Kilograms per meters cubed. So all of that, the rho times the bracket term is the amount of energy in that dV. And then you're going to add up by integrating all of the little volume elements across the control volume. So it's similar to mass. We're just picking up a little bit more in terms. And we're talking energy in terms instead of just mass. So similarly, the terms accounting for the energy transfers accompanying mass flow and work at inlets and exits can be expressed as all of that. So on the left, you've got the rate of change of energy, and that little e is specific energy. So that's energy per kilogram. Then you've got density, that, well, so the density times the dV, so the density is what, kilograms per meters cubed, and then the specific energy is energy per kilogram, and when you multiply it all together, you get the energy in that little volume element, and then you add them all up over the control volume, and then you take the time rate of change of that. Okay, so the heat transfer term and the work terms are similar, as already described. I don't think we have to go through those. And then at the inlet, we're going to do that area integral, and we're going to do it in terms of enthalpy, kinetic energy, potential energy. And then, so that's the energy content, that bracket, the inner bracket term, energy per kilogram. And then the rho V sub n dA is the amount of kilograms in that area. You multiply it all together, you get the energy that's crossing that little dA at this instant in time. You add it up all over all of the areas, and bingo. So anyway, I don't want to belabor this too much because we're not going to really work problems with this. But again, when you get into fluids, if you're taking your fluids class right now, you'll see this types of formulations, and later on in more advanced classes, you get into this sort of thing. So the change in the energy of a control volume over a time period can be obtained by integration of the energy rate balance with respect to time. Such integrations require information about the time dependencies of the work and heat transfer rates, the various mass flow rates, and the states at which mass enters and leaves the control volume. Okay, so I think right now I want to split off of this, and I want to look at a couple example problems. These are actually in your text, but I think they're pretty good. I meant to do this. These are on the mass stuff. I meant to do this, but I forgot before we jumped into the energy discussion, but that's okay. So let's just take a look. This is, like I said, these are a couple out of your book, but what the heck, it's an easy way to present it. So they're applying mass rate balance to a feed water heater. And feed water heater is a real device. That's in a steam system on a boiler. And what happens is you've got your condensate, you're making steam. It goes out to the plant. It gets used up at Frito-Lay in Frankfort, Indiana. They fry Tostitos. Plant smells so good. They're making Doritos and Tostitos and all this stuff. And they have their boiler pressure set to 400 PSI G. Got to be careful, it's PSI G, PSI A, because that saturation temperature, I guess 414.7 or something like that, gives them the ideal temperature for the cooking in order to fry those Tostitos. So what they have is they have a big fry kettle, and it's a double wall, big stainless steel thing, and they flood it with steam, 400-pound steam, and that steam condenses. It transfers heat into the cooking oil that has all the Tostitos in there just cooking away, and that's how they maintain a constant temperature in that cooking oil, because if they supply that with the same pressure of saturated steam, that temperature is locked. And so it's pretty easy to control steam pressures, and so that's how a lot of industrial processes are controlled. And so that steam then, hits that region between those two jackets, and it transfers heat into the cooking oil, because that cooking oil is losing heat out the top of the thing, and they're putting in cold chips, and they're taking them out all fried up and ready for us to chow down on. And so then the condensate falls out of the bottom of that, and it's initially at that same temperature, but it's way over there, and by the time we get it over back to the boiler house here, it cooled down a lot, And guess what? We didn't get it all back. Some of it leaked, and we got, you know, condensate leaks, and we might have some steam leaks. So we got to put makeup water into this thing. So we got cold water coming into the system, and that cold water's got a bunch of air and minerals and stuff. So we try to use softeners and clean up that water. And then, but the oxygen is still in there, and that oxygen is very corrosive at high temperatures. So we put it into this thing called a deaerator or a feed water heater. We put some steam in there with it. We heat it up, and that steam will drive off the oxygen, and then we actually vent a little bit of that steam to the atmosphere to get rid of that stuff. So anyway, that's a long story, but this feed water heater is a real device. Now, they don't have it all quite right, but they're trying to keep it simple at this point. So what they're going to do is they got a picture right here where, say, I got some steam coming in to heat this stuff up. I got my feed water coming back, and so we're going to heat this up to saturation, and I'm going to have saturated liquid fall out the bottom of it. Okay, so that, I mean, it's a pretty simple device. Now, in reality, you would have a little vent up here venting your non-condensable gases and oxygen, and a little bit of steam would have to go with it to get it out of there. But he decided not to put the vent on there. So, so let's see what he says here. Feed water heater operating at steady state has 2 inlets, 1 exit. 1 inlet, water vapor, steam, 7 bar, 200 degrees C, mass flow rate of 40 kilograms per second. At 2, we got liquid water, 7 bar, 40 degrees C, enters through area A2, which is, and he's going to tell you the cross-sectional area, 25 centimeters. And man, when you see cross-sectional area, you know you're going to be using this relationship right here. Anytime you see cross-sectional area, you might as well just make sure you got that relationship there, because it's going to come up. Saturated liquid exits at 7 bar at location 3 with a volumetric flow rate of 0.06 meters cubed per second. So we want to determine mass flow rates at inlet 2 and the exit in kilograms per second, and the velocity at inlet 2 in meters per second. Okay, so that's a description. I think I've given you that. That's a picture. So we're just going to mix this stuff together. We got liquid water coming in, we got steam coming in, and there you go. So engineering model. Say, here's this relationship. He's going to get it out early. Man, you just need to memorize that. You just need to memorize that. And remember that specific volume can be flipped up and turned into a density. M dot is equal to rho VA, or where rho is density, or M dot is equal to velocity times area divided by specific volume. Okay, so, you know, this is a conservation of mass problem. So there you go. There's our conservation of mass equation. dmCV dt is equal to the summation of the inlets minus the summation of the exits. Well, I got two innies and 1 outie, right? So there you go. I got M dot 1 coming in, M dot 2 coming in, and M dot 3 going out. I'm set at steady state, you know, someplace in there. I know it does. I can't find it. Anyway, because I know it's steady state because he set the derivative term equal to 0. It has to be. Well, that simplifies everything. So then, you know, then you can solve for M dot 2, whichever one you want to find in terms of the other two. So you got M dot 2 is equal to M dot 3 minus M dot 1. And here's this relationship between mass flow, volume flow, and specific volume. So M dot 3, and that's, now remember, that's cross-sectional area, normal or average, normal average velocity, and specific volume. Okay. All right, so, well, and where specific volume, that's 3, and we know that condition, right? It's saturated, okay? So we said we're saturated liquid at 7 bar. Well, okay, let's go let's go play in the tables for a minute. Make sure everybody still remembers their tables. Didn't get these opened up ahead of time. This one. So let's see. There's our temperature table, saturation. And here's our pressure table. And thank heavens it's in bar. I don't have to do any unit conversions. 7. There's 7 bar. That's the temperature, 165 C. And there's the specific volume. And remember, we got to move the decimal point, what, 3 places on this? Because this number has been multiplied by 1,000 to make it bigger to go in the table. Okay? So this number is 0.001108. Okay, so if we go back to this guy, there we go. 1108 times 10 to the minus third. So that's where the specific volume came from. And we're told up here that this flow rate is 0.06 meters cubed per second. Well, see, that's A times V. Because see, that's your volume flow rate. So see, some of these little things are simple, but until it becomes part of you, you go, well, crap, what do I do now? Well, you got to realize that 0.06 is A times V, okay? So now all of a sudden, you know this, so you know you can calculate the mass flow rate at 3. And so doing that, checking all the units, we get 54.15 kilograms a second. Okay, well, so what I got 40 kilograms per second of steam coming in, and I got 54.15 exiting. So the difference has to be what, m dot 2 over here coming in. So I just subtract those two, and I get 14.15 kilograms per second. And now I'm using this same relation to calculate the velocity at 2. So now I'm just going to turn it around and I'm going to solve for this velocity because I know, let me see, is that, give me diameter or, yeah, he gave me the area. So I don't even have to calculate area, he gave it to me. Okay. And of course, the other thing you have to do is, let's look up this specific volume at 2. It's 7 bar and 40 degrees C. Help me remember that. My memory is not too good. But okay, so at 7 bar, the saturation temperature is what, 165. Well, and now this is liquid. So should I use this same specific volume right here? Because this is the liquid column. Do I use that one?
This is below the saturation temperature.
I go to the temperature table because these things are strongly a function of temperature and weakly a function of pressure. So I don't use this. I go up here to 40, and I haven't checked this. I sure hope I find this number. I'm going to be embarrassed. 0.001078. I'll find the right one. There we go. 10078. So see, he took it from the table at 40 degrees C, not 7 bar. Okay, and that's our assumption. Now, if the pressure is super high, you can go look in the compressed liquid table and, you know, you may find it in there. But this pressure is not high and you're nowhere close. There's no point to do an interpolation for this. Okay, so then you're just plugging your value, your mass flow, your specific volume, your cross-sectional area, juggling your units a little bit, and we come out with 5.7 meters a second. So, I mean, that's pretty simple. Okay, let's go on to this one. This is a little better problem. This is a transient problem, okay? So what we're going to do here, let me make it a little smaller. We're going to be filling this barrel. Well, we're going to try to fill the barrel. We're going to see how high we can fill the barrel. So we've got, we're going to put in 30 pounds a second, but we got this pipe down here in the bottom, and somebody left the valve open. Now we're trying to fill the daggum tank. It's not going to work. We're not going to be able to get it all the way to the top. The question is, how full can we get it before we hit a steady state condition where we're putting in 30 pounds a second and we're draining out 30 pounds a second, as this thing, because it starts out empty. Okay. So let's see what he said. Water flows into the top of an open barrel at a constant mass flow rate of 30 pounds a second. Water exits through a pipe near the base with a mass flow rate proportional to the height of the liquid inside. So he's got this nice little relationship he's going to give us for m dot E. He says it's 9 times L, and L is the depth of the water above the bottom of the tank. You know, so wow, let's see how far we can get up here. Let's see. The area of the base is 3 square feet. Density of water, that's a good number to know. That's kind of standard. 62.4, 62.3 is standard density. That's pounds per cubic foot. So, you know, 1 cubic foot of water, you know, if you're an exercise guy, you know, say you want to do water curls, right? So you get you a cubic foot of water over here, and you get you a bar on that thing so you can pick it up. I can't do cubic foot water curls. I can't curl 60. I mean, with a bar, you probably got, what, 70, 75 pounds. I can't curl that much. I might get 35 on a good day, you know, if I really want to strain and grunt and groan. But anyway, it's good to know in a cubic foot of water, it's, you know, 62. And it changes a little bit with temperature. You heat that water up, that water's going to be a little lighter. The molecules spread out a little bit. So if that was 200-degree water, that might be, I don't know, 59 or 60, something like that. But it's someplace around 60, 62 pounds per cubic foot. Good number to know. Barrel's initially empty, plot the variation over time. Okay. Well, so here we go. There's our picture. We already did that. All right. So, well, what do? Well, you go to conservation of mass. dm CV dt is equal to m dot I minus m dot E. So, okay, well, how can we mathematically relate the amount of mass at any time t in this barrel? Okay. Well, we can take the volume and multiply it times the density. Well, so my area is 3 square feet times L is cubic feet, and I multiply that times density, and I'm going to get what? Mass. Okay? So that's all I got to do is rho density is constant, area is constant, and this L is a function of T because that depth's going to build at least for a while. Okay, so that's this. So I plug that in up here, and m dot I is just a constant 30, and m dot E is 9L. So I plug all that in. Oh my goodness, I got a little differential equation there. I'm not real good at this, but I expect you guys are experts on this, right? Right? Somebody shake their head. I want to see that. Yeah. No? Well, anyway. In thermo, this is about as bad as the differential equations get. So, you know, you don't have anything to be really concerned about. And they give you this as an example problem. So anyway, so rho and A are constant. So they pull out and we can divide through by them. And then we're going to pull the 9L term on this side because, you know, that's our variable L. So a few little manipulations and we get dL dt is equal 9 divided by rho A, which is a constant, times L is equal to 30 over rho A. That's a constant. And so, by golly, we can just write down that solution, right? 3 point, so what, if we take this constant divided into this, we come up with 3.33. And then we get a constant of integration times the exponential of the minus of this coefficient. And that's our solution. Not too bad. We've got to evaluate the constant. And so at time t, L is 0. And so if 0 at time t, that makes this thing 1. And so then C, you take this to the other side, so C is equal to minus 3.33. So you plug that in, and he sticks his numbers in for rho and area. And so you get this, and then you plot it up. So what? Eventually, what's this depth's going to go? This is going to decay away, this part. So our maximum depth is going to be what? 3.33 feet in this thing over time. It should reach there, if our analysis is correct. And then he's got this software, which if you buy the book, you get access to the software, but I know a lot of you didn't buy the book, so you probably don't have access. So I don't require that you do anything with the software. I mean, if you have access to it, you might want to play around with it. Okay, questions on that? Okay, so what do we still have some time here? Okay. Let's see. Well, we'll go back. We'll just go ahead. Where to get that in? Okay, so whoops, I can't spell volumes, can I? Well, that'll get changed in the next version I send you. Modeling control volumes at steady state. Okay, there's some notes here, some pointers, stuff like that. When mass and energy balances are applied to a control volume, simplifications are needed to make the analysis more manageable. You can't just, I mean, you have to make some assumptions to make the problems tractable. A careful step of listing assumptions is an important part of any analysis. Steady state operation is assumed, because that's the title of this thing. Flow is regarded as one-dimensional, where mass enters and exits the control volume. And at these locations, property relations are assumed to apply. So, you know, if things are changing too chaotically, we can get into that, you know, if we get outside the quasi-equilibrium assumptions, then we don't even have relationships among properties. And of course, that would be a deal breaker on most forms of analysis. Heat transfer term is sometimes set to 0, and because it is small relative to other energy transfers across the boundary of the CV. And so what are things that can make this heat transfer term too small so that we don't have to consider it? It could be, the surface could be well insulated. Huh. I got one of my little, I've got some little white dots around here. I'll get rid of that guy. Okay. Outer surface area is too small for much heat transfer to occur. The delta T, the temperature difference between the control volume and the surroundings, is very small. The gas or liquid passes through the control volume so quickly, there's not enough time for it to lose any heat. Okay, and where, I mean, you can, one good example of this would be a turbine, a steam turbine. You go up to a TVA plant and, you know, they've got maybe a Kingston TVA they have 200 megawatt units. they've got high pressure, intermediate pressure, low pressure turbine rotors all bolted together on a big shaft that turns this big generator that's probably, I don't know, probably a third of the size of this room. And that'll make roughly, 200 megawatts if you turn it. And it turns it at 3,600 RPM. Well, if you look at that high pressure turbine, which probably accounts for, I don't know, 25% of the thrust that's going into that shaft that's turning that generator. I mean, that thing, it's not any larger than this little module up here where I stand. And it's got insulating blankets on it. And when that steam is flying through that thing, it's pushing sonic velocities. So if you're a pound or a kilogram of steam and you're flowing through that thing, what opportunity do you have to lose heat in that turbine to the surroundings? Not much at all. First, it's insulated, and two, you probably spend a millisecond inside the turbine, and you're gone. So, now, if you put your hand on the surface, you lift that blanket and put your hand on the surface of that thing, that steam's 1,000 degrees. Yeah, it won't feel good. You won't leave it there long. But if you calculate the heat transfer rate compared, with the surface area and the delta T and all that sort of thing, and compare it to the amount of energy that's flowing through that device, you go, crap, it's 0.0000012. That ain't worth messing with. Not worth my time, So all of these things come into play. Now, so each individual control volume that you do an analysis on, you have to develop some judgment about, oh, that's going to be huge in this case. It's not so much in this case. So, anyway. Okay, let's see. The work term W.CV sometimes drops out of the energy rate balance because there's no rotating shafts, displacements, boundary, electrical effects, or other work mechanisms. Well, if you don't have any work going on, you probably should drop the work term out. That's pretty common sense. I got another one of those little boxes floating around there. When you do those little integrals in the equation editor, like when you're doing the integral over V, it wants another limit at the top of that. And so I just put a little white box around it because the way we're writing equations, we don't have it. Yes, sir.
Another question. On a system like a tank where you've got a piston, like on one where the piston pushes in and out.
Yep.
Is that considered a work?
Oh, absolutely.
Okay, so that would be a work.
Oh, yeah. That's boundary work. Because on a piston cylinder, we usually consider the mass inside like a control mass, and then so maybe we shoot some heat in, or maybe there's really an explosion. But in thermo one, we try to keep it simple. We don't do explosions. They do that later because explosions are complicated. So we just say, oh, there's an instantaneous injection of heat to simulate the explosion. And so then that's going to cause the gas to expand, and it's going to push that cylinder up. And absolutely, that's that gas doing work on the surroundings, right? Because everything except the mass of gas is the surroundings. And so it pushes that piston up, absolutely. That's what we call PDV or boundary work, for sure. Good question. Okay, the kinetic potential energies of the matter entering and exiting are neglected when they are small with respect to other energy transfers. We almost always, now I say that, there are some, they gin up some problems here, and you have problems already assigned to you where you have to include, I don't know that we're including the potential energy term much, but the kinetic energy term, if you've got high flow rates of gases or things like that, then you have to include that kinetic energy term. So sometimes that gets included. In practice, the properties of control volumes considered to be at steady state do vary with time. They certainly can, but so this is the little discussion that comes with this. If let's say this is pressure versus time for a control volume. And so you can see that A over there, you know, we just got some kind of random fluctuation. But I mean, it's not huge. And so if you had data, you could average it out and probably just use that average pressure in your calculations. And life would be pretty good. You know, your boss might well accept that, you know. Don't show him the plot, he'll be good with it, you know. Now, I mean, but, or it could be a periodic fluctuation where it goes up and down like that. And, you know, so you have to see if you think that's causing any, the highs and lows are causing anything serious to change in the system. But if it doesn't, then, you know, it's probably okay to use an average in that situation too. Okay, these are comments about those figures. The steady state assumption would still apply when properties fluctuate only slightly about their averages or in cases where periodic time observations are observed. The steady state assumption can apply to control volumes if the following are satisfied for each period of operation for a cyclic device. So that could well apply to this B over here condition. There's no net change in the total energy and total mass within the control volume, and the time average mass flow rates, heat transfer rates, work rates, and the properties of substances crossing the control surface remain constant. Okay, let's see what we got up here next. Yeah, okay, I'm gonna cut this off today. I'll give you a few minutes. Next time we'll start going through these various devices and looking at example problems and maybe working some of the problems that have been assigned to you. We'll walk through the application of the equations to them and then look at some examples. Okay? So very good. I'm going to cut it off here. I hope everybody has a great day, and we'll see you on Thursday. I'll get the lecture posted later on this afternoon or tomorrow. Thank you very much.